Alright, time for another DraftPhysics.com video presentation. DebatePhysics.com also, where you'll find a collection of the average video, or well, frankly, the more concise and direct videos on the particular subjects. Anyway, but you won't find much debating in terms of the counter arguments to the actual arguments I make by explaining on this board. So I will eventually get to some Ian Gostling arguments, you could call them, but they're really not relevant and not on the subject. So the subject is momentum versus mv squared, 1/2 mv squared, the living force, as it was called by its originator, who, by the way, invented the theory some months before Newton published his most prestigious work that actually explained the gravitational constant and the motion of all the celestial bodies in great detail, and quite successfully, that is, accurately. And so there is a bit of it's an extraordinary challenge in the sense. It certainly challenges what Newton published, and clearly nobody fell for it. That's just the truth. Not almost nobody. Because it didn't make any sense, and it didn't fit with everything Galileo and Descartes and Newton had provided as a foundation for the function of mechanical things in the universe. They understood it as quantity of motion. That's their word for energy. And basically the rule is that forces control this motion, and that the force is completely proportional to the motion. You put a certain amount of force in, you get a certain amount of energy out. And so the force is energy, and you can store it, or you can jump in a stream of it. Anyway, so that's the background. Theirs is the challenge to the existing theory, and it should come with pretty substantial evidence. I shouldn't say they need extraordinary evidence, but only ordinary evidence would do, and they don't even have that. So they make claims like it takes 4 times the fuel to go twice as fast, and yet in 350 years we have zero evidence that that's a truth. Alright, so it starts sort of with gravity. You could argue this is why Leibniz, believed what he believed, is because he saw something, that looks like. And, scientists should say, yes, platypus looks like a duck in some respects, but they can figure out through other means, it lays eggs, and it's got webbed feet, it's got a bill, maybe it's related to ducks because it's got so much in common with them. But then again, it's, got the fur, and it's heavy, and, it's got things that tell you it's not a duck, And the same is true in this, observation. And I can do this with rolling objects. So again, this is an argument that my detractors will not explain. They will not explain how it actually works. And they're saying my drawing of it is inaccurate. And I'm making a mistake, and I misunderstand. That's what the physics Michael guy says. And I'm simply arguing, no, you completely misunderstand and distort, because you won't bother looking at the actual evidence. So when you drop things, they acquire quantity of motion, And in gravity, you get it whether you're dropping or not. So even when you're not dropping, you can feel the fact that you're hitting the earth. Just a fact. So you might not see yourself moving, but you kind of know you must be in some respect, because you keep pushing into the ground. You can't do that if you're not, if there isn't some energy, something pushing you in. So anyway, I could drop 2 objects, and it would take 4 times the distance to get me twice the velocity. And the key is it's only going to be twice the time, and I'll plainly state you're only going to weigh twice as much when you hit the ground. Alright, those are important numbers. So yes, this is 4 times the distance, but it's only twice the energy. And this is the key reason, and this is the key thing that Newton discovered, is that you fall at a rate of 9.8 meters per 1 second. 1 second. Not any second, not 50 seconds, not 90 seconds. In 1 second, you do this. So obviously, this could be a quarter of a second or a millionth of a second. It doesn't matter what the period is. You just change the number. So if I made it 2 seconds, it'd be 19.6. If I made it a half second, it would be 4.9. You just change the number relevant to what kind of speed you're talking about. So let's just say in this example, this takes 1 second to fall this distance. This only takes 2 seconds. And it's basically this event will be exactly the same as this event. And this event, okay, will in fact be exactly the same in terms of what you're going to get. You're just going to get 9.8. You're going to get 9.8 in this distance, and you're going to get 9.8 in this distance. And this is what Newton and frankly Galileo figured out first. He just didn't have these numbers. But he knew this is what it was doing. Okay, is that it's how long you're in the force will decide how much of this force you collect. So like a spray paint or anything else, it's an inverse square kind of relationship. The closer you get to the light bulb, the higher the density of photons, the more photons will hit you. Same thing is true here. It's the same for any force that basically either goes to a point or leaves from a point. It's the inverse square law. So that was the other part that Newton added to this. That was the constant. Was that knowing that constant, you can just go to any location and distance and you can know exactly what the force rate is. So anyway, this is the truth Newton revealed in terms of, yes, it's 2 units of time, therefore 2 units of force, therefore that's why you have 2 units of velocity, and that's why you have 2 units of momentum or weight, is because you collected 2 1-second units of force. Now in the rolling object example, it just clearly is showing you again how gravity works, because it's exactly the same truth. Let's understand, you're going half the speed here. You have half the velocity at this location, not in the middle, at this location. So in the first little drop, you're already going half the speed, and you'll only increase your speed by 1 unit of speed in this whole entire 3 units of distance. These are facts. Okay, and the same is going to be true here. You're going to roll 2 objects, one with twice the velocity. Well, the fact is it's going to go half the speed here at 3/4 of the distance down the track. That this event, this 1 unit of velocity object, will roll 1/4 of the distance. And the fact is that this event here at the halfway point will be exactly the same. This essentially is the same velocity as this. It's the same experiment. Just remember that this whole section here, okay, you only lost half your energy here. You lost half your energy here. You were in the gravity, okay, an amount of time here, and it equals the amount of time here that you were in the gravity, creating friction. And the simple explanation is the same amount of force is hitting you, paint, over this large area, and the same amount in this small area because of the time. It's the same time you were in the rain. You got just as wet here in this distance because you walked slowly as you got wet here when you were walking fast. And that's the simple explanation, is you're putting less force per foot into the ground here, and you're putting more force per foot into the ground here. The friction is not linear or the same per foot. It's the same per unit of time. Alright, so these 2 experiments, yes, they superficially look like, well, that must be 4 times the energy because it went 4 times the distance. You know, that must be collecting 4 times the energy because it traveled 4 times the distance. So yes, you could be fooled, but if you understand what Galileo did, Descartes did, and Newton did, you understand that these are the true facts. Okay, and the true fact is the platypus has genetic code making it a marsupial, not a bird. It's just a fact. Don't get fooled by the superficial appearance. Whales aren't fish. It's just the truth. Yeah, they swim somewhat like one. They do certain things like a fish, but they're not fish. Okay. All right. So I think and then in the 1700s, when this was resurrected as an idea, okay, even though these experiments weren't highlighted as much because they had already been debunked, and it had been pointed out that levers don't work and different things won't work. They did some clay experiments where they dropped round things into clay and then stated that therefore, because the round things indicate the same 4-to-1 relationship, and again, it seems like, so therefore it must be like, but that was just merely because they didn't understand that the deeper you go into the clay, the more efficiently you get rid of clay. So the faster you're going, the more energy you hit with, the more you gain an advantage, because you're doing less of this, pushing the clay down, and then over, and more of just over. Just over. Pushing it sideways is a lot easier than pushing it down and then sideways. Almost any idiot could understand that. So anyway, that experiment was a gimmick, and that was all. That's the history of 1/2 mv squared in terms of somehow everybody fell for it. But it's just superficial. It only looks that way. It isn't really that way, and it's really not hard to understand. It's 9.8 meters per 1 unit of time. 1 unit of time. Not 10 units of time, not 400. This 9.8 only works if you use 1 second. Not 2 seconds, not 10 seconds, not a half a second. 1 second. And you have to change this number if you're going to change the unit of time. Period. And if you do it accurately and correctly, you can clearly understand there are only 2 units of force here. There's 1 unit of force here. That's why there's all these 2's here. It's because this only has twice the energy. Because it only received twice the force. Alright, so we'll use that as a background for part of this video. And these are the arguments that haven't been touched. Now we'll go to the function of springs and levers. Okay, so I'll pause and erase. Okay, so this sort of started in terms of making it obvious to me that this living force was not correct with a simple experiment where you just take, it doesn't matter, a 5 mass object. And you move the 5 mass object with a velocity, and for the sake of clarity and simplicity, we'll make it just 10. My marker is running out. Anyway, so this is going at 10 velocity, and I combined it with this 5 mass. I add a 5 mass to it in the most efficient way possible. Okay, Velcro, whatever. And then I end up with a 10 mass object, and it's only going 5 velocity. So I've conserved what's called momentum, what Newton would call energy if he had the word, what was called the quantity of motion. I've conserved it, the MV. So everything looks fine, no problems really, except by their formula, 1/2 mv squared, I now only have 1/2 the energy. So somehow I lost what I had here, that this can't do what this did. So this has been degraded substantially. Alright, and so somehow the argument is I conserve all the momentum, they'll concede that did happen, but somehow I lost half the energy, and they'll say I broke pieces off. And they flew into space in some direction, and I made heat, and that flew off as entropy, a complete loss of that bit of energy. It's going in some other place. As Descartes would say, it's not part of that system anymore. It's loose. Okay, it's free. It can't be over here and over here. So if it's doing heat, unless you make the heat come back and go back into the object and move it, it's lost energy. You can't recover it. It's lost momentum. It takes momentum to make heat. It takes momentum to fly pieces off. The momentum has to come from somewhere. You can't keep your momentum and have momentum going off in all these other directions. You can't still have your momentum in this direction and say, yes, you're also moving over here, and you're also moving stuff over here, and you're moving stuff over here. You can't do that, okay? So it simply is paradoxically nonsensical to say I could break things off and shoot them into space and I keep my momentum. Can't do that. That's a violation of conservation law, okay? So an illustration of this would be, let's take that 5 going 10, and we'll just make it a ball or whatever, an object. And I'm just going to throw it onto a spring, and now it's going to compress the spring a certain amount. Okay, it's a fixed amount. It will compress the spring. All right, it's a unit of compression. Now, if I uncompress the spring, I have the expectation I'll get this energy back. So it goes in, compresses the spring pushes it back, I get back my 10 and 5, I get back my momentum. Their argument is that this is energy, okay? It's not momentum, so it's 1/2 mv squared. So instead of being a number like 100, it's a number like 250. Okay, well anyway. So their argument is that all I have to do is find something else to put in front of this spring, because I have to conserve the kinetic energy, in their opinion. And what could I put in front of this spring that would equal a 5 mass going 10 in terms of its kinetic energy? Well, I could actually put I could put 2 10s here. Sorry. They're saying it has twice the energy of this. That this has twice the energy of a 10 going 5. So they're saying that I could put 2 10s here and have the expectation that they will come back, okay, with the 5 velocity. So I only lose half the velocity. I've doubled, tripled, quadrupled the mass. Because they're saying it's 4 times the energy. Now, do you really think I could throw a 20-pound object? I threw a 5 object in at 10, and I can get a 20 going 5? We haven't seen that experiment, and I don't think we ever will see it, okay, because it doesn't happen. The spring conserves the momentum. I put the 10 on here, I'm just going to get 1 10 coming back with 1 5 because I'm going to conserve the momentum. I'm not going to conserve the kinetic energy. So these are rather simple experiments, right? I mean, they should be doable. Compress a spring the same amount, put in some kinetic energy with a light object, then put a heavy object on and see if you lost all the kinetic energy. See what kind of kinetic energy you get back. And vice versa, of course. They're saying basically that I can, well, they're saying it, but it doesn't happen, right? Again, I'm stuck because if I take the 10 mass going 5, they say it only has half the energy and it won't produce a 5 mass going 10. So they're saying if I put the 10 mass in, I can't get the 5 out. At the higher velocity, that this will only be going 7 velocity. Now again, we don't have these experiments, but you can just rationally understand that doesn't make any sense, and it breaks all kinds of conservation laws. Momentum and kinetic energy are fundamentally opposed theories. They have nothing, there is no compatibility. Nobody can argue it's just semantics or something. This is a real contradiction. Anytime you attempt to convert the energy or force in one object, and you do it to an object that has a different mass, either larger or smaller, you will fail, okay, to be able to conserve the kinetic energy. In the case of going to something smaller, you're going to gain huge amounts, and in the case of something bigger, you're going to lose huge amounts of kinetic energy. Now, obviously, gaining free energy is something we can't do. So, to the lever. Or the spring, frankly. I mean, I'm not as convinced springs are perfectly conservative, but I'm quite convinced levers are. Alright, so as I think might be conceded by those who would defend the kinetic energy theory, and somehow they have some counter argument that I have yet to hear, in light of the fact that I did in fact do the experiment, you can put a mass 1 unit of distance, and then you could put a quarter mass, 4 units of distance, and basically have a circumstance where you have 4 times the energy, in terms of its kinetic energy theory, oscillating on one side of this oscillator than the other side. So they'll concede it does perfectly oscillate. I mean, I showed it. It does perfectly balance in the first place. So this is a 1/4 weight, and this is a 1 weight. And it perfectly balances, and you can oscillate it. You can give it a little bit of energy and it'll oscillate for quite a while, indicating by the rules of oscillators that the energy is merely moving this way, and then it goes back this way, and then it goes back this way. And so there really technically has to be the same energy on both sides, because one side's use of the energy is being stored in the other side's position, and that they will just switch which one has the potential energy versus the active energy. The active energy versus the stored energy, however you want to describe it. The positional energy. So indicating that, yes, momentum perfectly works. It makes perfect sense. This goes 4 times the velocity because it's 1/4 of the mass. No problems at all. This moves, in the same unit of time, 4 times the distance that this unit. And this is called mechanical advantage. So if you actually use this lever without the masses, and you just use it by moving the fulcrum to create the same effect, all you're really doing with mechanical advantage is converting momentums. You can do a very light but fast motion out here, and cause a very heavy but slow pressure on a heavy object. So you could push a rock or something by only applying a small amount of pressure over a higher velocity. Or I shouldn't say pressure. Weight. No, I can't really say weight because weight is mv already. Mass, frankly. So you can apply that mass over a velocity, and you'll just convert it into, you go from a big M to a little v, and just perfectly convert into a big V and a little m. And that's all the lever's doing, is converting. Now they call it mechanical advantage, but there's no real advantage in the sense that it's really the same thing. You're just using the one that's circumstantially to your liking. Either a high volume, at a high volume at a low pressure, like a high voltage at low amperage, or high volume at low volume at high pressure. So you're pushing it very fast, comes out of the hose very fast, but it's a small volume, but you're collecting it because it's very fast. And you have the slower volume, so you could do this with water, you could do this with hydraulics, it works with all kinds of things. Alright, so their argument is these levers do not conserve momentum. That's not their mechanical advantage, and that somehow, even though it oscillates perfectly, this will not leave, with 4 times the velocity. That sometime if I put a force in, and I'm doing this conversion, that is, this thing's going to decelerate, this force is going to decelerate, and this is going to accelerate. Depending on where I put it, it'll accelerate slowly here, faster, 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 faster. So depending on where I put it, I can perfectly match the force coming in to the force going out. Now if I put this in some other location, I'm going to break that, and it's not going to have this continuity, it's not going to match, and you're going to get a bounce or some other thing. The argument is if you do it right, nothing will bounce, the deceleration will perfectly match the acceleration, and you'll get a complete conversion of the energy here into the object here. So you put a force in, and the simple factual truth is you're going to get the same force, the same momentum out, okay, but just in a different mass to velocity ratio, a different amount of mass to velocity. You're going to do the conversion, and this has to leave. So in the oscillation, it's moving 4 times the speed. If I put in just enough energy to get this to fly off, their argument is the speed reduces, and now it's only 1.4. Well, in this case, we have to make that a bigger number because we're doing 4 times. So 1.4 of 4, 2 points, whatever, something. They say that's what the speed will be. Okay, that somehow it will lose speed. So it's going 40 miles an hour, and somehow when it leaves the lever, it's going to go 30. That's their argument, somehow. That's all I can get out of their argument, because they won't make their argument. They won't draw this lever and explain how it works. Alright, so I think that's all that I need to premise it with this time. But again, all these arguments, these drawings, these images, these illustrations, these figures, they won't counter them with their own explanation for how it works. And the reason why they won't do it is because they can't do it, because it will be demonstrated to be nonsensical. They won't be able to do it in a sensible and logical way, because their energy is gremlin energy. They'll have to draw a gremlin. They'll have to draw pixies. They'll have to draw some angel that makes the thing do something extra. They'll have to show where the angels deform the metal and the angels shoot the piece off. Angels did it because the momentum obviously couldn't have done it. Yeah. Alright, so now we will move on to a couple of that are no doubt junk videos, but we'll play them anyway, because this is all the opposition can produce, is this junk. Alright, back we are. So we'll do this energy stored in a spring concept. So I did do a live video yesterday, so if you didn't see that, the way YouTube does it, you might not know unless you look in the category of live that there was a video done. But I did do a response to a Lasco guy, or whatever his name is, that really wasn't that on the subject. He just provided some more, I would say, irrational rationalizations, and for me to have to debunk. And that's all the people can do. They won't debunk what I drew. Okay, so click on this and see what this garbage is. Alright, we'll probably need more volume here. We'll see how that is. So, energy stored in a spring concept. Let's see, I don't think there's any description. It doesn't appear to have any description. Let's see. We'll just read some of this Brozo thing and see what he says. Well, I personally found this helpful, even though I realize springs don't store energy in the simplistic way Gary imagines, whatever that means. I mean, it's sort of a known fact how they do it. I mean, the thing is made out of little domains. The atoms are stuck to each other like little bubbles. The fact is, those bubbles slide across each other, and when they do that, they become magnetically uncomfortable. Alright. It was very helpful to see it compared to energy stored in an example that is linear. That'll be fun to see, yes, where it was stored linearly. This is memorable, I don't know, and that helps a lot. So this is obviously just mushy mush. You have some great ideas for explaining things in a clear way, so he's not going to explain anything. I've already debunked whatever he's going to say, right? He's saying a spring has 4 times the energy when it's twice compressed. And the simple argument is it only takes 1 unit of energy to put one object on the scale. And it only takes 1 unit of energy to put the second one on. Twice the compression of the scale can't possibly be 4 units of energy, because it only takes 2 units of energy to create the weight that'll do that. I mean, I could have drawn that too. Let's see, I'm not sure if the following idea also works. I'm picturing a guy walking along picking up weights as he goes. So they'll come up with some nonsense where, of course, you can make anything take more time and therefore be more work. You can slowly get into space and use 10 million times more fuel, or you can go into space really quickly and use a lot less fuel. Those are your choices. You can lift a dumbbell at the speed the dumbbell would free fall, which is the ideal lifting speed, to minimize its total weight. You want to make it weigh less, okay? Have less gravity hit it. That's the ideal. You don't want to throw it over your head, so you don't want to use more energy than you need. And the ideal amount of energy is exactly the free fall rate. Lift it at the free fall velocity, and you'll be a big winner. Alright. I mean, these people are really just so stupid. Okay, so we'll come back to the second half of that. So this will be nonsense. So again, I have also drawn and illustrated the simple argument that the faster you go over a surface, that was in the friction argument, the faster you go over it, the less you're going to weigh. So if I put a scale in the road and people ran across it, the less contact they have with it, the less they can possibly weigh. So the faster they go across it, the less the needle deflects, indicating perfectly that there's less energy going into the ground.
Trying to show why the energy stored in a spring is not linear.
So it is perfectly linear in the sense that whatever you put in terms of an MV, you're going to get back out. And you have nothing to demonstrate it works any other way. It can't possibly conserve kinetic energy. Because if it does, that means you can move 20 pounds 5 miles an hour. Go ahead and show me that experiment.
As in Hooke's law, which is about the weight and displacement.
So again, it's this silly pulley weight argument where I've pointed out already, numerous videos, numerous times I've stated this, and he's just going to ignore everything I said. So every single thing stated he's going to ignore. It's about how long it takes this weight to fall will decide how much energy it has possibly collected. So if something stops you from free falling, it means you're in the gravity longer, and it means that energy is now part of what has to be consumed by either the thing stopping you. Well, really, that's the only choice, right? Because you're not moving if it stopped you. So it has to absorb all the energy. All the energy from gravity that hits us when we're sitting here, when I'm making this video, the ground is absorbing all of it. I don't get to keep any of it. It takes all of the voltage, all of the, however you want to think about it. I'm connected to the ground wire. The ground is absorbing all of the electricity. I can't keep any of it. Duh.
This is a little example of our little guy walking along this distance here. He's got a harness on and he's lifting a weight through gravity.
So this is the same exact experiment that Physics Michael did in the sense it's in the reverse, okay? He's somehow walking, he's pulling the weight up against gravity. So I've just explained, it's a 9.8 meter per second force. It's about how long, okay, the force is hitting something. That decides how much energy is absorbed. And if the thing keeping the object from moving, okay, the thing deciding how fast it's moving, okay, is the only thing you're tied to. That string is only tied to that weight. So what the weight does will be exactly, has to be dictated by the force applied by the person. The faster the person gets the weight to the pulley, the less energy he'll have to use. The slower he walks, the more work he will do. This is the same as lifting the weight very slowly. You're going to do a lot more work. You're going to sweat. Now, the conventional physics says it's no work, which is a ludicrous statement on its face. But clearly that's what's going to happen. You're going to have to absorb all the gravitational energy. So 1 second, 2 seconds, 3 seconds, 4 seconds worth. If you do it in 1 second, then it's only 1 unit of force you had to overcome. If you do it in 4 seconds, well then it's 4 units of force. Duh.
Now as he starts walking along this distance, the force required is constant.
No, it isn't. It's only constant if his velocity is constant. So if he walks at a constant rate, then the force will be constant, and guess what? Your time is going way up. So the amount of force you're going to have to overcome is increasing. Is higher than it would be, okay, if you could move at a quicker speed.
I mean, if we showed this on a graph, this is the distance.
So again, these graphs are retarded, right? I've pointed out you can't multiply a cause times an effect. There's no sense in it. You have to mix. If you're going to bake a cake, you have to mix ingredients. You can't put a cake in the ingredients. Okay, you don't make cake out of cake. You make cake out of ingredients. All right, and this distance thing is exactly correlated to the velocity thing. It's basically the same thing. Velocity causes distance. There's absolutely no point in multiplying them times each other.
D, as he walks along. And this is the force on the side. There's 10 pounds of force required.
Right, so the force is the cause of the distance. It's just multiplying a cause times the effect. It's not sensible, it's irrational, it's useless, it will tell you absolutely nothing except now you've just multiplied a thing times itself. The distance is an exact consequence of the force. Now you're just multiplying the force times the force. You're not doing anything sensible.
Required to start, because this is a 10 pound weight. So as he walks along, it's a 10 pound force constantly applied, doesn't increase.
Okay, you can say it doesn't increase, okay, but the fact is the longer you take, the more 10 pounds you're pulling. The fact is the slower I lift the weight, the more work I have to do to lift the weight. I mean, it's just so obvious. So you want to tell me that it isn't more work if I take 3 hours to lift the weight, I didn't do more work? Do you really want to say that? You really want to defend that position, that I can't make it more work. Of course I can make it more work by just doing it slow.
Base. The whole distance.
I want more paint on the surface. What do? I keep the thing in the paint sprayer longer. Duh. The longer it's in the paint sprayer, the more paint's going to be on the surface. If I don't want paint on the surface, I want to keep it as clean as possible. Well, then I go through the paint as fast as possible.
This is work times distance, or force times distance.
So, okay, so as pointed out by Galileo and then Newton, obviously it's time in the case of gravity. Time is the unit determining how much force you'll have to deal with. It's clearly, obviously, force times time. Distance does not create your exposure to the force. You can do the distance really slow and get a ton of force. You can do the distance really fast and get very little force of opposition. So again, he's just ignoring the argument that has been made and made no rational counter argument how Newton really meant it's about distance, and that Galileo meant it's about distance, when everything they wrote and did and examined pointed to it being about time. It's 9.8 meters per 1 unit of time. And in this case, 9.8 per 1 second of time. Not 1 year, not 1 month, 1 second.
Equals work. The area under this line represents the work done. It's a constant force. Now the difference.
So it's absolute nonsense, right? There's just no point in arguing it. It's nonsense. It's about the time. Now, in this case, if you're moving at a constant velocity, the time and the distance will perfectly correlate. But you're not going to go 4 times the distance here. There's no evidence that your d number gives you 4 times the distance. So I don't even know why you're making this argument. Because in this particular case, you're not going to travel 4 times the distance.
It's with, if he's going to, our little man now, where has he gone? If he's going to walk along the same distance, compressing this spring, the graph would look something like this. He would start off very little force applied to the spring, and as he started to walk along, obviously the spring's getting compressed.
So obviously that's not the truth, okay? It's the same force being applied. So in a sense it's linear as you go. You're just increasing. I added another 1 block. I added 1 block. I added 1 block. I added 1 block. I added 1 block. 1 unit, 1 unit, 1 unit, 1 unit. And yes, your collected units of force are increasing, but you're only adding 1 unit, 1 unit, 1 unit.
So it's exerting more force against our man. He's having to do more.
All right, he's saying the spring is exerting a force against the man. It's really not. The man is exerting a force against the spring, and the spring is absorbing the force. And it won't be until the man stops pushing that the spring can push back.
Work to compress the spring as he moves along, will apply more force. So on this axis is the force. So the line is going up at this sort of angle.
All right, so there's no point, right? I mean, this is a decisive argument against what he's saying. He's trying to contrive some idea that putting this second weight on. So I have 1 pound. I'm going to put this second thing on, and it's going to go, and I only have 1 pound, and I have 1 unit of energy. So the 1 pound is only 1 unit of energy. That's it. And when I put this second one on, all of a sudden now I have 4 units of energy. I only put 1 more pen on. I didn't do anything more than that. I did 1 unit of force. I added 1 unit. How can I have 4 units now? I'm just saying it's a decisive argument. You're not going to be able to unravel that and say that isn't true. It's absolutely true. This can't possibly be 3 times the energy I'm adding. This can't add to 3. This only adds 1. This only adds 1. 1 unit of force per pen. There is no, oh, this pen has to do so much more work. No, it doesn't have to do any more work. They do the work collectively.
And then you would say that the work done is underneath this line. And you can see that for every
compression of the spring, I only get 1 unit of force out. I compress the spring with 1 mass. I get 1 mass of reflex. It can only push 1 mass. It can't push 2 masses, at the same velocity. So it's clearly 1-to-1 relationship. 1 unit of force, 1 unit of action. 2 units of force, 2 units of action.
Distance, we compress the spring. The energy stored in the spring is not the same as this example. Every distance we move along, the energy stored in the spring increases in a linear way.
I don't even know, there's no spring there, and I don't know what you're talking about, but whatever. There's no difference. There's just a force. 2 things are going to interact with each other, and they have different vectors. And those vectors are just going to mean that there'll be a sum, and the sum momentum always works. So again, this isn't explaining where momentum fails, and he's certainly not going to show us this great evidence that it fails. Like I say, he's done some experiments, but they all have very noticeable and unaccounted for flaws.
Because he's lifting a weight through gravity. But by compressing the spring, every distance our man moves along, he's storing more and more energy because the force
It's not more and more, and so you got to use more explicit language. You're saying he's increasing the amount of energy in the spring beyond the amount of weight he applied. So somehow this only weighs a pound, and yet you're saying somehow it put more than a pound worth of energy into the spring. No, it didn't.
wire is increasing as he compresses the spring.
Alright, so let's just make sure you understand. I have played their videos. 95% of all the videos they've made, I've played them and I've responded to the parts I say are inaccurate or unproven and all that kind of stuff. They won't do me the same courtesy. They won't play the argument I made at the beginning of this video. They won't play those points and respond to them. Now they might play them and ignore them, but they won't play them and respond to them. Alright. So, to the other video. I mean, that was just useless, right? I mean, it's not a counter argument in any way. He's just saying, imagine the spring has put 4 times the force in. Well, why don't you show me it launching something else with now 4 times the momentum? Where are you going to show me evidence of this 4 times the energy you've put in the spring? It's not going to push the items back with 4 times the energy. It's not going to show us 4 times the energy. Anyway, so I mean, it's just junk. It's just a little fable he told that, yeah, you know, again, rationalizations work because they don't have to be true. They're just talk, and talk is cheap. And you know, for 350 years, that's all they've done. He's done a bunch of cheap talking, and they haven't done any experiments. So this is what is a balance. Now, the only point in having a balance is to, you know, you can have balances that are very, very sensitive in the sense that it either balances or completely fails, you know. Or you can have balances that will oscillate and be a little fudgy. You have balances that'll stay in positions and tell you exactly how uneven the things are. So there's all kinds of ways to configure the balance to do different things. But the very idea is that it's just saying, depending on where you put objects, you can change their weight. You can change how their exposure to gravity is interpreted.
Back on the balance. We love the balance, don't we?
So he's done all these experiments, and what he won't do is the simple experiment of just make a lever, okay, and then put a known quantity of energy in and see if you can do the inverse mass to velocity ratio. Find the spot where you get the inverse mass to velocity ratio and see if you conserve the momentum. They won't do this simple experiment that would prove levers don't conserve momentum.
That's a rotor. Now you'd say that was balanced.
So he says that's balanced. When, well, obviously it's demonstrating that one side is being interpreted as heavier than the other side. That's how it's being interpreted.
Say that's balanced.
So it's broken, okay, as a mechanism for comparing the two weights, because now it says the two weights are always the same. Yeah. I mean, it's basically saying in this case that this weight is somehow heavier than that weight. So you could, if you did a scale and you're trying to test whether somebody's giving you some gold and you're measuring the gold by a standard on the other side of the scale, you don't want a scale that does that, okay, because then you can obviously cheat.
Would you say?
So even though it's the same mass, you're going to be arguing, hey, look, see, the scale says this side is heavier, when it's not really. So anyway, scales aren't made this way. That's why their stuff is always hanging from the scale, is because it doesn't work this configuration. Alright, we already established that. Who cares? So again, in spite of the fact that I've repeatedly said, who cares? How does this prove kinetic energy? How does this prove levers don't conserve momentum? I want to see you prove that levers don't conserve momentum.
That's balanced. Yeah, I would. It's just not balanced in the horizontal. When these weights center of mass.
Well, if a scale doesn't show you balanced in the horizontal by every common understanding, that means there's more weight on this side. So people wouldn't call that balanced.
Masses pass straight through the pivot. It'll balance or find static equilibrium, I suppose is the technical term, in any position. It's in
Yeah, I'm just not sure. That's fine. I'm not sure as if you could make the fulcrum minute enough that will no longer be true, because it just might have to do with this little tiny difference of spreading the fulcrum over a larger area. And if you spread the fulcrum over a smaller area, pinpoint, then maybe it won't work anymore. But who cares? Like I said, I'm really not. I really just don't need this detail. Okay, I can tell that the platypus isn't a duck without this.
equilibrium. There's no net moment or force acting on this system now. But
Okay, so let's understand. It's silly not to say there's no force acting. There's no differential in what it's perceiving from the force. The object is clearly in gravity. It's constantly being hit by gravity, but gravity isn't detecting any difference in the two sides of what's on the snail. It's not seeing any difference.
if we drop these weights down here, below the axis of rotation, centre of mass below, it balances perfectly in the
Yeah, and now if you just move it a little tiny bit, it'll oscillate, it'll be okay. See, but the problem is these can't swing. So now you're still with rigid weights in rigid arcs. So as you start moving further up, again, you're moving the weight sideways more than you're moving the weight up and down, the higher you go up in the arc. So that's where gravity can no longer be a storage device when you start going sideways.
horizontal position. It's in static equilibrium again. But if now we displace it,
So again, he always displaces at this 45-degree angle. So just give it a tiny oscillation, see what happens.
and let go, will it stay there? Will it stay in static equilibrium in this position? No. It'll oscillate.
Because the masses are below. Now if you put the masses above, then you're really going to start getting into trouble, because now you have the weight higher than the fulcrum. The center of the whole lever's mass will end up higher than the fulcrum, which means now it can tip. That would be part of the Julius Sumner video explaining that yes, the lower you have these weights, the better for preserving its capacity to stay in an oscillating mode.
The interchange of forces and moments. Until
Moments.
it finds its
Baby talk.
static equilibrium.
It's obviously not in static equilibrium, so it's obviously oscillating. And if he had put a 10 mass here, okay, and let's just say these are 5 masses. If he put the 10 mass here, it'll oscillate just as perfectly. So that's a fact. You put a 10 mass, a twice as heavy mass right here, it'll oscillate just as well. And you're stuck with the very fact is that this side will be oscillating with twice as much energy as this side. Now you won't be able to hit it and feel that energy because the whole lever is the weapon, so you won't be able to feel it. But if you let the masses go free, that is, you have a little explosive device that explodes and frees the mass to it just disconnects the mass from the rest of the lever. The mass will continue with the velocity you gave it. So when you break it free from this side, you're going to have a piece of energy, a piece of matter with twice the energy than when you broke this one free. So that's all the argument is. If I do the experiment and first it's oscillating perfectly, and then I free the mass, it can now go, it's free liberated. And so whatever momentum it has, it's now going to have, it keeps it, whatever MV it has. By your theory, okay, the one side, when I do it one way, I create twice as much energy as if I let the other one free. It's paradoxically nonsensible.
But, so it's also a balance. What happens if we do that? Put the weight, centre of mass, above the axis of rotation.
So it matters on how heavy your lever is and how heavy your masses are, because the whole system is now what you're measuring. And you're saying, have I put the center of mass of the whole system above or below the nail? I think that's the only thing that matters.
It's a balance again, though. Static equilibrium. What happens now?
So he put enough energy in that the oscillation is now too much. That's the simple truth. So the first motion has too much energy in it and pushes it right past where it's balancing in the gravity, and then when it's not in gravity at all. I mean, moving sideways isn't a gravitational issue. Moving up and down is the gravitational issue. So once you go past a certain point, gravity can't recover, because gravity doesn't have much influence in the horizontal motion. It only has influence in the up and down motion. So if you put less energy in, so let him balance it and then just poke it a little and see if it recovers. Just give it a little poke, see if it oscillates. And that'll tell you that it's really just about how much energy you put into it. It's a tolerable, it's an acceptable oscillator as long as you don't put too much energy into it. And that's the whole point of the weights being above, is it just makes it unstable. It doesn't make it unusable.
Turns over, oscillates.
And it oscillates with a lot of energy because you frankly put more energy into it by allowing it to go all the way past and keep the energy for one rotation.
Has won the battle. It will come to horizontal static equilibrium. Well, I enjoy these experiments.
Okay, they prove nothing. It's completely irrelevant to a conversation between whether that lever conserves kinetic energy or whether it conserves momentum. Doesn't mean a damn thing. Doesn't have anything to do with the subject. Who cares? Except him. I mean, they're propagandizing that somehow this should impress me, that this should prove something to me. It proves absolutely nothing. I never, like I said, I don't need to detail, any of this. It's completely uninteresting. How is this going to dissect whether it's a platypus or a duck? Whether it's a marsupial or a bird. This isn't going to explain. This is just pretending you're proving something when you're proving nothing. Nothing relevant.
I don't know if anybody else does.
Well, I certainly don't, so why am I being included in this somehow? I don't see how it's at all relevant to momentum and kinetic energy. I don't see any relevance at all. Alright, now we'll go back to the comments. and find out why this is relevant. Yeah. Can somebody explain why it's relevant? Oh, the Merker. Lying scumbag. Okay, let's see. He also says he's going to sue me. Good luck with that. Yeah, it's okay. You don't think you're suable. Okay, you don't think there's laws in your country against slander and libel. Okay, we'll find out, won't we? Okay, he always goes pro se. Well, that's why I said when I get the money. Because then I'll go, I'll have a lawyer, merely for the point of forcing the judge not to be a lying piece of scum. Because, they have to do the bar exam kind of, they have to be procedurally, they can't fuck lawyers as much as they fuck pro sayers, okay? Regular citizens have very few rights, and you seem very proud of that, okay? But whatever. I'm just saying, I won a federal appeal pro se. So, you can think I don't know what I'm doing and all this bullshit, but there's not too many people that win federal appeals pro se, who aren't like prisoners or something. It happens very rarely, buddy. Okay, and he will need foreign counsel. Well, frankly, no, you don't need counsel to file papers, fuckhead. I can file the accusation, okay, and I can file the evidence against you, and then you'll have to make your argument. That's what happens from front of the judge. The lawyers are there just because regular people don't speak lawyer very well. But it's really just about an argument, okay, and then a judge makes a decision based on the arguments, and the arguments have evidence attached to them. And the evidence will be, clearly you're a butthurt little weasel, okay, who's going to try to attack me, okay, because I said something about you don't like. That you're a jerk and an idiot and a moron. Those are legal things to say. The things you've said are illegal. Okay. And to show up in Canada, so again, showing up is another thing you don't really have to do. Okay, for the suit. Not going to happen. Alright, I'm just saying, you're saying you can lie and slander and libel me with immunity. So I'm saying you're providing me more evidence to present to the judge. See, he doesn't care. He thinks he's above the law. He thinks the law doesn't apply to him because a pro se can't defend themselves. He's overtly saying, I have contempt for the law. So bravo, moron. Thank you for the more evidence you just gave me about how trivial you're taking your violation of the fucking law. Okay, American courts don't have jurisdiction over Canadians. Guess what, though? They can basically call you guilty, and you'll never be able to get a passport, okay, without answering the claims first, all right? So if you never want to come to America, you never need anything from America, then go ahead and talk that arrogant shit. Because basically I can get you barred from ever coming here, fucker. Okay, online comments, and thus refuse to enforce an American judgment. No, they'll enforce it. They have to. So if I get the court to say, yes, he appears to be completely guilty and he's unresponsive to the claims, and so, yeah, fuck you, Canadian. That's what the judge can say. Yeah, you don't have any right to violate our laws, okay, with immunity. That's what the judge is going to say. You don't have immunity, fucker. You're not some kind of diplomat, you fucking weasel. Okay, good luck, fool. Yeah, fuck you, fool. You just gave me more evidence. Thank you, you dumb fuck. Yeah, bravo. All right. Even the very fact that he's defending his actions, which is lying about what took place when I filed a lawsuit against a fucker who's, painting swastikas on my images, the ones I own. Okay, that's not fair use. Fair use isn't painting swastikas on other people's image, you fuck. That's what he's endorsing as tactics. Fuck you, piece of shit. So you're outing yourself, jackass. Ian, I hope you've seen my comments. They got blocked, but hopefully you know what you're dealing with here. What a whining, wussy pussy shit of a piece of crap human being. I indulged you for weeks. Weeks of nonsense. Weeks of it. I indulged you, and I kept telling you, I kept warning you. You know, I'm really not here to tutor you. All right? I'm not going to sit there and explain to how to use the toilet paper and wipe your dumb ass. Okay? That's not my fucking job. Go watch a video explaining how to wipe your ass. You retard. And you just kept doing it, you troll. You don't have an identity here. You don't do anything. You don't put up anything. You're just some vague screen name. Ugh, weasels. Thank you. I am going to keep trying to tell the truth. So he says he's telling a truth somewhere. This wad of shit, okay, who hasn't paraphrased my arguments correctly and who can't make any relevant on the subject. Okay. Who sits there and says, tell me what you predict this experiment will come out. I do exactly that, and then he weasels out and he doesn't do the experiment. And then on top of that, he's telling the truth, he says. So even though he shows us the scale and he shows it on a big metal bar and that there's every indication he already did the experiment, he's pretending he doesn't even know what the results are. He doesn't even know what they are, and yet somehow he believes, oh yeah, Gary must be right. Obviously, because that's the only reason why he wouldn't do the experiment, right? If my prediction wasn't correct, why would he not do the experiment? I mean, come on, he'd want to prove me wrong, wouldn't he? Amazing, right? Just absolutely amazing. These people are so dishonest. Okay. When you run into a scale with 9.8 meters, well, no, you can't really run into it with 9.8 meters per second, okay? That's the velocity for exactly that, 1 second. So when you run into a scale, you can run into it with different velocities, okay? But the only velocity to read your weight when you bang into a scale horizontally, right? So you're going to bang into a scale horizontally. What you need is the same speed that would double your weight this way, because you're taking away gravity. So you're just going to say that what's my motion weight that creates that much deflection? And the fact is that's 1 centimeter. Or it's 8 to 10 millimeters is the height you need to double your weight. So that's what doubles your weight. So you need the velocity that you have when you fall 10 millimeters, a centimeter in gravity. So whatever that is, whatever that speed is that you reach when you fall 1 centimeter, that's the speed you have to hit the scale this way to read your weight. So the speed you're going when you fall 1 centimeter is the speed that will create your weight on the scale. Just making clarification. All right. Yes, I enjoyed them too. Neat arrangement. I don't get it. Okay, yes, Ian's experiment really tips the balance. In what way? I don't know how this is relevant to anybody. How does anybody find this all that intriguing in this conversation about something so important as, is momentum real, or is 1/2 mv squared the real definition of energy? How is it relevant to that conversation? I can't find the relevance. Hi there, Ian. Hope you are well, mate. If you enjoy having a play around with the balance, place one of your weights in the down position below the center line and one in the up position above the center line. How fascinating. Well, I can't bear the anticipation. I can't bear the anticipation. It's only going to increase the problem, I think, so it'll just fall even faster. Depends on what side you lift, I guess. No, I think it does. If you lift the side that's hanging down, you'll be okay. You lift the side that's hanging up, it's going to be a problem, I think. But anyway, it doesn't really matter. It might even just compensate for each other. They might undo each other's effect, and it goes back to being a regular balance. But again, it just has nothing to do with kinetic energy. Just nothing. Alright, so that's it. It's more than enough, frankly. And so I don't think there's anything new from the other pigeon shitters. Let's see. Brozo hasn't done anything, I don't think. Nope. This insanely insipid, energy collection method. You just couldn't get sillier. You just really couldn't. Alright. So that'll be all, folks. So the arguments in the beginning of this video are the arguments I want them to debunk. I want them to show how 9.8 meters per 1 second means per 1 foot. Okay, that's what I want them to show me. Or 1 meter. That somehow distance matters. Time doesn't matter. That's the simple thing they need to counter-argue. Alright, so till the next time and such and so forth and what.